Hey, Algebra 2 Honor students, this is the start of our next unit. Unit 6 is going to involve a lot of factoring techniques that we're going to see coming our way and eventually some solving of equations. So all of what we do today should look very familiar. Actually, at the very beginning of our school year, we did recap some of these factoring techniques together. So if we take a look, I'm only actually going to do these 5 examples with you. That's it. It's a short video today. And then next time I see you in class, we're going to be practicing with a little mix of all of the techniques that we're about to see. If we look at something like number 1, what I think would help us is if we look at this as one term and this is a second term here, they both have something in common. They happen to have that quantity x plus y in common. And if you don't like the way that looks, you could use a dummy variable. You could say, let the quantity x plus y equal something like j. Try not to use the same variables as what you see here. So what would that turn into? 5a times j minus b times j. And then what happens in this case is you can take out a j as a GCF. And that leaves you with 5a minus b. And the advantage to using a dummy variable is, just in case you don't see that x plus y itself as a GCF to factor out to start, now that I have that j factored out, we can replace j with the quantity x plus y. And remember that the whole goal of factoring is to write something as a product. And now that this is written as a product, that is the final answer for number 1, x plus y times 5a minus b. All right, moving on to number 2, we have 2 terms here, so a little different than actually all of the others. This is the only one that I see that has kind of just these 2 distinct terms. We have 49 and then 25, and those are standing out as kind of special numbers to me because these are perfect squares, right? C to the 4th is also a perfect square. So knowing all of that, I guess the best technique for something like this would be the difference of perfect squares. So as a reminder, the pattern is think about taking the square root of each of these. And we should be pretty good at that based on what we did in Unit 5. So this would be 7 minus 5c squared, and then 7 plus 5c squared. And the last thing I want you to think about when factoring is, can you break these down any further? Could we have continued to factor either of those? And the answer in this case is nope. So difference of perfect squares, when you recognize it, we can use this strategy to break it down. And again, if neither of those are factorable, then that's your final answer. Moving across the way to number 3, x squared minus 17x plus 30. This is your really traditional trinomial factoring. When you factor something like this, some students refer to it as the AM method. We're looking about what adds to negative 17 and factors that multiply to positive 30. And you can make a list of 1 and 30, 2 and 15, 3 and 10, 5 and 6. But in the end, the factor pair that works would be x minus 15 times x minus 2. Right? Those 2 things multiply to positive 30, and they also add up to negative 17. So that hopefully the trinomials in this format are pretty easy for you to factor. Taking a look at number 4, this is a little bit more complicated in the way of factoring because this is also a trinomial, but we have that lead coefficient of 3. So the first thing I would ask myself is there a GCF to factor out of that? And that's actually the first question you should ask yourself for all of these. GCF is the first technique we have to consider, but it turns out that there is no GCF that's in common with all 3 of those. So in order to factor this, you can either use a model called guess and check. Some of you might know the model slip, divide, slide, but maybe more of you are familiar with this box method idea. So if we kind of reverse box method this, we want to think about 2 things that would multiply to give you 3w squared, that first term. And the only possibilities that I can think of are 3w and 1w to make that happen. And if you know anything about box method, when you multiply to get this trinomial here, we know that the values that I pick here and here have to multiply to give you negative 15, which is the last term of the trinomial. So to get negative 15, it's some combination of 1 and 15, or it could be 3 and 5, where one of them's positive, one of them's negative. So what we have to double check on here is these 2 boxes, when I decide on which factor pair works best, have to combine to give you a total of negative 4w. Okay, that's kind of the most important piece here. So you have to do a little bit of playing around with placement, right? If I put a 3 here, this product is 9w. If I had put the 5 up here, then this product would have been 15W. So it makes a big difference as to where we place the 3 and the 5. But actually, I think I kind of like the 3 up here and then the 5 down here. Because look at what happens. 3 times 3 is a 9W. 1 times 5 is a 5W. And if I were to able to make this one negative, negative 9 plus 5 is negative 4. Well, we can make that negative by writing W minus 3. And therefore, 3W has to get combined with plus 5. So when all is said and done, the final answer after doing this box method practice would be 3W plus 5 times the quantity W minus 3. Okay, so we have to be really good and proficient at factoring using this, and maybe you didn't have to go through the whole box method process. Maybe you can kind of just visualize in your head what those factors are, and that's of course fine too. But if you struggle with examples like this, setting it up in a box format I think is really helpful. All right, going over to number 2, if you see something like this, it's tempting to want to square this, distribute a 2, distribute a negative 6, and it's going to start getting real messy. So I'm going to use a strategy for this last example, just like I used up here. Number 1, let's use a dummy variable. Let's let x equal the quantity a plus b. And again, the only reason I didn't use x up here was just because we already had x in the expression. So this turns into 2x squared minus 6x minus 20. Right? Replace those a plus b's with x's. So again, we're faced with a situation where we have that lead coefficient in front of x squared. However, compared to this one, notice how 2 is a GCF of this trinomial. So that's going to make my life a lot easier to factor out 2 as a GCF. You get x squared minus 3x minus 10. And then from there, we can hopefully factor the trinomial a little bit further and continue to completely factor here. So x squared minus 3x minus 10, that would actually break down to x minus 5 times x plus 2. And this is factored, and we have to do one more step. It actually is completely factored, except for the fact that we have to make our dummy variable replacement here. Okay, so in the last and final step, we're going to replace every x with the quantity a plus b. So it's a plus b minus 5 and a plus b plus 2. And this is certainly the most complicated of our cases here. It's not that the factoring is challenging. There's a lot of room for error, I would guess, but dummy variable is a good start. Take out the GCF, factor as much as possible, replace in the end with the dummy variable. Oh, and by the way, that GCF of 2, don't forget to carry that down to the last and final answer. So this is a good mix of all the factoring strategies I want you to be super confident with. And the next time I see you, like I said, all we're doing is practicing with these ideas. Factoring trinomials, maybe some lead coefficients in front of the trinomials, difference of perfect squares, GCF, and some dummy variable thrown in the mix. Okay, that's it for today. Next time I see you, lots more factoring to do. Have a good one.